Hello and welcome to this calculus lesson. Today we're going to start talking about the chain rule for taking derivatives. This is in section 3.7 of our text, but sometimes functions aren't simply functions. Sometimes they're functions inside of other functions. And this will help us find the derivatives of those. And the rule in math is true. If you do something using one method and you do the same calculation or evaluation using another method, they should both come out to be the same thing. And we're going to start by looking at that. Like, why do we need the chain rule anyway? What problem is it solving? What's wrong if we don't use it? So we're going to take a look at evaluation derivatives of compositions of functions using the chain rule and the notations. We're also going to evaluate derivatives using the chain rule using Leibniz notation. So Newton's and Leibniz notation. Newton's notation, the dy over du, dy over dx, he writes it as an actual slope, change in y over change in x. Leibniz uses the single quote at the end to indicate a derivative, f prime of x, we would say. So consider the function, some function of u is the sine of u, and u is x squared minus 4. So you've got this function here, sine of u, and you've got x squared minus 4. So if f of x is sine of u, and g of x is x squared minus 4, if you go back to your pre-calc, you know that the composition of functions f of g of x, or sorry, this should be f of u. I wrote f of x, should be f of u. F of g of x is simply function f is a sine, and inside you're going to have an x squared minus 4. So in this case, sine is the outer function, and x squared minus 4 is what I'm going to call the inner function. So taking the derivative of this function here, yes, you need to take the derivative of a sine function, which would be cosine. You get the cosine of x squared minus 4. But you're not quite done, because that only tells you how y changes with a change of 1 with x. X squared minus 4 changes by 1. You want to know how y changes when x changes by 1. So you then have to multiply that by the derivative of what's inside. That's the fundamental idea behind the chain rule, is when you take the derivative of sine of something, you're telling, you get the cosine of the same thing, but this only tells you how y changes when x squared minus 4 changes by 1. You want to, and that changes by 1 is not quite conceptually exact, but you want to know, you don't want to know how y changes when x squared minus 4 changes. You want to know how y changes when x changes, so you have to multiply that by the derivative of what's inside, which would be the derivative of x squared minus 4, 2x. So we're going to look at this with a polynomial first and see, like, why do we need the chain rule? It'll be clearer if I look at x squared minus 4 squared, for instance, and taking the derivative of that. So if we take the derivative of, sorry, I'm using a different format here. If we take the derivative of 6x minus 10, hopefully by now, and hopefully at this point, you're all very comfortable saying, oh, the derivative of y dy dx is going to be just 6. It's the slope of this function. The derivative of the negative 10 is a 0. The derivative of 6x is 6. Hopefully that's like, you just know that. Now look at this. This, if I multiply this out, is also 6x minus 10. So the derivative of, so we're saying this is u. So y is 2 times u. dy du would be 2. du dx would be 3. If I multiply dy over du by du over dx, the algebra works as if this was a over b times b over c. These reduce, and I get the change in y with respect to x, which is what we want generally when we're looking for a derivative. So I can just multiply the 2 times the 3, and I get my 6 that way. So this is taking what's a simple function and turning it into the inner function is 3x minus 5. The outer function is you're multiplying something by 2. So we say that's 2u, where u is 3x minus 5. I can take the derivative, just consider 2 times something, derivative of that is 2, and then take the derivative of the inside, and 3, I multiply those together, and I get the correct derivative. This is how you take the derivative of a composition of functions. You take the derivative of the outer function, and you multiply by the derivative of the inner function. This is a very simple example, though. We're going to see some other examples by the time we're done. Once you get the basics of this, you're really going to want to look at a lot of examples. And I'll try to point out the pitfalls as you go, like what common mistakes do students make. That becomes an important thing to understand. But if you think of the derivative as rate of change, if y changes twice as fast as u and u changes 3 times as fast as x in this situation we did in the second case of the composition, then y would be expected to change 6 times as fast as x. That's the most basic example. So this is really, this is what we're looking for when we're looking for derivative. We're looking for this dy dx, the derivative of y with respect to x. But if I have y expressed, in the case we just did, I can take the derivative of the outer function, which this is 2 times something, so I'll just get a 2, times the derivative of the inner function, outer function, inner function. I can multiply those together and it becomes dy dx. And you can see from this notation that even algebraically it becomes dy over dx. These are fractions. If you handle these as differentials, that works. In Leibniz notation, when you have one function inside another, so you have some function and inside of it is some other function, the way you take the derivative is you take the derivative of the outside and you keep the inside the same as it was in the beginning of the problem. You don't do anything with the inside, but then you multiply that quantity by the derivative of the inside. The mistake students make is they do the derivative of the outside and the inside together. They take the derivative of the outside function and then multiply by the derivative of the inside function. Unfortunately, in the example we started here with just factoring out that 2, you actually could do that and it would work, but that won't work regularly. So I'm going to go over to the second page of notes here, which I have to go over to the right to do that. And we have another example. Now, I want to take the derivative of this using, so if I had this, up until this point in time, if you had something in parentheses like this, there was always a 1 there. And you didn't, you're saying, well, why didn't I have to use the chain rule? Well, you didn't have to use the chain rule because the derivative of the inside was a 1. Here I have a function inside of another function. I see that, and I can see that the derivative of the inside, I'm sorry, I don't know why this keeps doing that. The derivative of the inside here is a 3. So let me focus on that. The derivative of the, okay, that's good. So this is like y equals u squared, where u is 3x squared plus 1. You probably did some exercises like this in pre-calc 1, where you separated out functions and wrote them as composite functions. This is why. You need to be able to see that there's a function here inside that's squared. So the outer function is something squared. The inner function is 3x squared plus 1. The derivative of y with respect to u is 2u. Now notice that inner function has not changed. The derivative of u with respect to x is 6x. That's the derivative of 3x squared plus 1. I multiply these together. So I get 2u times 6x, and say, well, wait a minute, that makes no sense. There's no u's in my problem. Well, change that u to a 3x squared plus 1 times 6x. The derivative of the outer function was something squared. You bring the 2 down, you subtract 1 from the exponent, but notice the inside stays the same. It's still u. It's still 3x squared plus 1. 2 times 3x squared plus 1 to the first, that's your power rule, times the derivative of the inside is 6x. Now, if I multiply all that out, I get 2 times 3 is 6 times 6 is 36 x cubed plus 2 times 6 is 12 plus 12x. If I multiply out 3x squared plus 1 squared, I get 9x to the fourth, that's 3x squared squared. 1 at the end, that's 1 squared. 6x squared in the middle, that's 3x squared times 1 doubled. If I FOIL this out, I have to, this is 3x squared plus 1 times 3x squared plus 1. I get y equals this up here. So this here and this here are the same function. So I should get the same derivative. Let me change pen colors. So when I do the derivative this way, I have 9x to the fourth. 4 times 9 is 36. X was a 4, now it's a 3. So I bring the 4 down in front, multiply it by 9, reduce the 4 by 1. Plus, bring the 2 down in front, multiply it by 6, reduce the x by 1. The derivative of 1 is a 0. So this is my derivative if I multiply the function out. And this is my derivative if I use the chain rule. And they are the same. If I only wrote 2 times 3x squared plus 1 and said, there's my derivative, I would not be the same. It would be 6x squared plus 2. It would not be the same as this. What would be missing would be the derivative of the inside. I would have to multiply everything by 6x in order to get them to become the same. So the chain rule means you break the function. You take the derivative of the outer function, leaving the inner alone, and multiply by the derivative of the inner function. So I kind of want to stop. I'm going to erase this in a moment. I think I'm going to erase this. I'm not as good with this software as I am with others. Oh, there we go. I want to erase at least pieces of this so I can have some room on the bottom one. You can always stop the video, go back. Okay, so let's try the next example, and I kind of want to get all the extra stuff out of the way here. So the next example. Again, I have a function inside raised to the 100th power. So we're not going to raise something to the 100th power. We'd be expanding that forever. It'd take us longer to do the expansion than the test would take. Or by the time it's done, our project is over, right? So I'm going to use the chain rule because it's not feasible to expand this. Now, for this problem up here, you could choose to do it either way for me. Doesn't matter to me. You could expand it or you could use the chain rule. But here, you're not going to have a choice. So this is y equals something to the 100th power. So the way I get the derivative of y with respect to u is it's 100 u to the 99th power. And what I have to remember is u is what was inside, so u is x squared plus 1. That's my something. I know that's a very sophisticated term. The derivative of u with respect to x, u is x squared plus 1, is going to be 2x. So what I get is 100 u to the 99th times 2x. Now you have to replace u because we only have one variable. You know what u is. You know what u is in terms of x. Now some of you are already seeing this pattern where I can start with the outer function. I take the derivative of the outer function. That gives me the 100 here, the 99 there. I don't know why I got a triangle out of that, but there's 100 there. And it's also not going to erase that. That's weird. 100 there and a 99 there. And then I'm not done. I have to, so notice the inside stays the same. I have to multiply by the derivative of the inside when I'm done. So I get 100 parentheses x squared plus 1 to the 99th times the derivative of x squared plus 1, which is 2x. And then you can write this out as 200x times x squared plus 1 to the 99th. So you're not always going to have to write out u to the 100th and write this all out. Once you see the patterning, you'll be able to go right to this step here and then simplify. Do not go right to this step here. Do this step here that I'm showing and then simplify. All right, let's move on and see what our next example is. And I think our next example is probably down and over. There we go. All right, so now here's some student practice as far as breaking these up. You pause the video, and I want you to find out what the inner and outer functions are, basically. Break this up into y is the function of u, and u is the inner function. I would start by defining the inner function maybe. So try that. Don't take the derivative, just break these up. Stop the video and then come back. All right, you're back, so either you're cheating or you've done this. So here I see the inner function is 6x minus 5, so y equals u to the 4th, and u equals 6x minus 5. It might be easier to identify the inner function first. This one's a little more complicated. This is where the value in doing this is we get some more complications. I see an x plus 1 inside of something. So I'm going to define that. I'm going to say u is x plus 1. Sometimes it's easier to define the inner function first. So y is 1 over the square root of x, of u. Okay, so you can take the derivative of u, and what you're going to find is we have a chain rule piece that's simply a 1 here. Here, I'm going to define u as x squared minus 1, and y is the square root of u. This one, be careful, this is tangent of something squared. Note, if you're going to square the trig function, the squaring, and we'll see in the next example, goes right next to the trig function. This is, I'm going to say this is the function inside is pi, which is just a number, times x squared. Y is 3 times the tangent of u, once I define u that way. So if I replace u there, I'll have back my original. So I know how to take 3 times the derivative of 3 times something. It's just 3 times the derivative of tangent will be what I'll do there when I do take derivatives. Cosecant, I am going to strongly recommend this. You rewrite. I want you to rewrite all of these problems. What this means is cosecant of x cubed. I am going to suggest that every time you have this exponent right next to the trig function, you rewrite the problem first. Because now I can see that cosecant, that trig function cosecant of x is my inner function. And what I'm doing to cosecant of x is I'm cubing it. So hopefully, I know dealing with trig functions, you're not quite as comfortable with those yet, but you really need to be able to understand them. And, you're taking the tangent of something, you're taking the cosecant of something. And in this case, in the bottom, then you're cubing that. So whether the cube is inside the parentheses, we call this part here the argument. In this case, if there's no parentheses, the x is the argument. So if the argument is squared, that's one thing. But if it's right next to the trig function that's squared or cubed, you're cubing the whole thing. Okay, so that's a piece you need to remember from prior work. So I'm going to stop this right here and make a part 2 to this video where we continue. This is the idea of an inner function and outer function. This whole video gets at that. We're going to look at the inside-out rule and the outside-in rule after that. Okay, so thank you for joining me, and we'll see you in the next video.